4 patients were taken off life support at the University of Michigan in 2023. Doctors expected silence. What they got was the opposite. 2 of those brains didn't go quiet. They surged. Gamma waves, the fastest electrical activity your brain produces, the ones linked to conscious thought, to memory, to the feeling of being aware, spiked to 300 times their previous levels, higher than anything measured in a healthy, waking person. Those brains were more electrically alive in death than they had ever been in life. The circuitry that did it, the gamma wave architecture that lit up in those dying patients, is inside your skull right now. It has been there since before you were born, sitting in the folds of your cortex, doing nothing at this intensity, waiting. Over the next 35 minutes, you will see what your brain is programmed to do in the moment it loses everything. Recordings exist, data exists, and by the end, you'll face a question you can't answer. Does your brain shut down when you die, or does it finally turn on? Your brain has never done what it's capable of. The one time it will run at full power is the one time you won't be around to notice. Or maybe, noticing is exactly what it's doing. But before we get to what that means, we need to start with the night the first recording happened. Because nobody planned it. Nobody was looking for it. A machine built to watch for seizures caught something else entirely. In 2016, an 87-year-old man was admitted to a hospital in Tartu, Estonia. He had developed epilepsy. Late onset, sudden, the kind that appears without warning in older patients. His doctors connected him to continuous EEG monitoring, electrodes placed across his scalp, a machine tracking every electrical whisper in his brain 24 hours a day. They were looking for seizures. They wanted to know when the storms hit so they could adjust his medication. For several days, the machine did its job. It recorded spikes. It recorded calm. It drew the familiar jagged lines of a brain under observation. Then the man had a heart attack. It wasn't expected. It wasn't related to the epilepsy. His heart simply stopped. And in the minutes surrounding that moment, before, during, and after cardiac arrest, the EEG kept running. Nobody turned it off. Nobody thought to. The machine had no concept of what was appropriate. It just recorded. Dr. Ajmal Zemmar, a neurosurgeon affiliated with the University of Louisville, was part of the team that later analyzed those recordings. What he found in the data made him hold the paper for 6 years before publishing. He wanted to find another case, another recording, some confirmation that the data was real, not an artifact of the epilepsy, not a glitch in a dying machine monitoring a dying man. He never found one. In 2022, he published anyway. The paper landed in Frontiers in Aging Neuroscience, and the data was unambiguous. In the 30 seconds before the man's heart stopped beating, his brain produced a massive coordinated surge of gamma oscillations. Organized, structured, rhythmic activity in the frequency band between 25 and 150 Hz. The exact range associated with the highest cognitive functions humans possess. Concentrating, dreaming, meditating, retrieving memories. The oscillations your brain produces when you remember your mother's face, or relive a conversation from 20 years ago, or become suddenly aware of your own existence in a quiet room. Those oscillations exploded across this man's cortex in the seconds before he died. But the gamma waves weren't alone. The EEG showed changes across every frequency band, alpha, theta, delta, beta. And they weren't random. They were coupled. One type modulated the others. The brain wasn't just firing, it was coordinating. Different regions talking to each other in patterns that resembled, in ways Zemmar couldn't explain away, the patterns seen during active memory retrieval in healthy brains. His brain appeared to be replaying something. Zemmar put it carefully in the paper. The brain may be playing a last recall of important life events just before we die. He stressed the limitations. Single case, epileptic patient, possible confounds, every caveat a scientist is supposed to include. But privately, the question that haunted him wasn't about methodology. It was simpler than that. If a brain can coordinate a structured memory replay in the seconds after the heart stops, after blood pressure crashes, after oxygen delivery fails, then what does that say about the moment of death? When does dying actually begin? When does it end? And who exactly is doing the remembering? Because the heart stopped, the blood stopped. The man was, by every clinical metric, dead. And his brain was doing the most sophisticated thing it had done in 87 years. The recording in Estonia was a single case, an accident that happened once and was never repeated. Zemmar searched for 6 years and found nothing comparable. One data point does not rewrite neuroscience. But Zemmar didn't know something. On the other side of the Atlantic, someone had already found the same signal, in multiple species, across 15 years of work. And it started with an accident of her own. In 2008, Jimo Borjigin was studying hormones. Specifically, she was interested in the pineal gland, that tiny structure buried deep in the center of the brain that regulates melatonin and helps control sleep cycles. She had rats wired up at her lab at the University of Michigan, monitoring chemical output, running routine experiments on circadian rhythms. Nothing dramatic, nothing unusual. Then, one of the rats died. This wasn't the experiment. The experiment was about sleep. But when the rat's heart stopped, Borjigin's instruments were still running, still measuring the chemistry of the brain in real time. And in the moments before death, one chemical spiked so hard it broke the scale she was expecting. Serotonin, a flood of it. The molecule every major antidepressant targets poured through the dying rat's brain in quantities that dwarfed normal waking levels. Borjigin's first thought, as she later told The Hill, was simple. She wondered if the rats were hallucinating. Most scientists would have noted the anomaly and moved on. The experiment was about sleep. The rat was dead. There was nothing to follow up on. No grant, no framework, no field called What Happens to Brain Chemistry at the Moment of Death. That field didn't exist yet. Borjigin didn't move on. She ran it again. More rats. Same result. Serotonin. Every time. Every rat. The dying brain was executing a chemical program. In 2013, she published her first major paper. She euthanized rats with carbon dioxide and monitored their brains with EEG, the technology that would later catch the surge in Estonia, though that recording wouldn't happen for another 3 years. What she found matched Zemmar's data before Zemmar's data existed. Within seconds of cardiac arrest, the rats' brains erupted with gamma oscillations, highly organized, intensely coupled between brain regions. The rats were comatose, their hearts had stopped, and their brains were producing activity patterns consistent with conscious processing. There is no gentle way to say that. A lot of people, she said, assumed the brain after clinical death was inactive, hypoactive, fading to black. We show that is definitely not the case. But serotonin and gamma waves were just the surface. Borjigin kept pulling the thread, because there was another molecule she wanted to find, one that had been a rumor in neuroscience for decades. DMT, dimethyltryptamine, the most potent psychedelic compound known to science. In the 1990s, psychiatrist Rick Strassman had written a book called The Spirit Molecule, hypothesizing that the pineal gland produced DMT and released it at the moment of death, flooding the brain with the compound responsible for the most intense altered states ever documented in humans. Shamanic visions, entity encounters, the dissolution of self. The experience, as Strassman's clinical subjects described it, of leaving your body entirely. It was a beautiful hypothesis. It was also completely unproven. Nobody had ever detected endogenous DMT in a living brain. Strassman admitted it was speculation. Borjigin contacted him. She said, "I study the pineal gland. Let's test it." In 2019, the results came back. DMT was there, in the living rat brain. At concentrations comparable to serotonin, dopamine, and norepinephrine, the brain's primary operating chemicals. But the truly destabilizing finding wasn't that DMT existed in the brain. It was where. Strassman had guessed the pineal gland. Borjigin found it there. But she also found it in the neocortex, in the hippocampus, in the regions of the brain responsible for thought, memory, and spatial awareness. The two enzymes required to synthesize DMT weren't locked away in one tiny gland. They were distributed across the thinking, remembering, experiencing parts of the brain. Your brain can manufacture the most powerful psychedelic compound in existence. It has the raw materials right now, distributed across the structures you're using to process this sentence. And in dying rats, DMT surged alongside the serotonin, alongside the gamma waves, all at once. A coordinated chemical and electrical explosion, as if the brain had a protocol, a sequence it executed when the body failed. Something that looked, from every angle Borjigin could measure, like the brain doing something on purpose. By 2023, she had what she'd been working toward for 15 years. Humans. 4 patients at the University of Michigan, whose families had agreed to withdraw life support while EEG was running. 4 brains, monitored at the moment of death under controlled conditions. 2 of the 4 showed the surge, gamma waves erupting in the temporoparietal occipital junction, the region neuroscientists call the hot zone for consciousness. One patient's gamma activity reached 300 times baseline. The other surged less dramatically, but in the same region, with the same coupling, the same organized rhythm. The other 2 stayed quiet. Borjigin noted this too. The surge isn't universal. Not every brain goes out with a storm. About 46% of critically ill patients who die show it, across all studies. The other 54% don't. Nobody knows why. But Borjigin had the chemistry and the electricity. She had rats and humans. She had 15 years of data pointing in one direction. The dying brain is not failing. It is executing something. A program, a sequence, a final act of organized activity that exceeds anything it produced while alive. What she didn't have was the experience itself. No EEG or chemical probe could provide that. What does it feel like to be inside a brain running at 300 times its normal gamma output, while DMT floods the cortex and serotonin saturates every receptor? Is there a feel like at all? For that, Borjigin needed someone who had been there, someone who had died, experienced whatever the surge produces, and come back to describe it. She needed 567 patients, and a doctor willing to ask them what they saw. Of every 5 people whose hearts stop and who are brought back through CPR, 1 will tell you that death is something else entirely. Something no religion, no philosophy, and no medical textbook prepared them for. Dr. Sam Parnia has spent his career listening to these people. As the director of resuscitation research at NYU Langone Health, he runs the largest clinical study of consciousness during cardiac arrest ever attempted. It's called AWARE. Awareness during resuscitation. And the data from its second phase, published in 2023, is the kind of data that makes you read a sentence twice. 567 patients, men and women whose hearts stopped while hospitalized, all received CPR. Fewer than 10% survived to leave the hospital, but among those who did survive and could be interviewed, the stories followed a pattern so consistent that Parnia stopped calling them near-death experiences. He calls them recalled experiences of death. Because the patients weren't near death. Their hearts had stopped. Their blood pressure was 0. By every clinical metric we have, they were dead. And they were having experiences. Lucid experiences. Structured ones. Organized narratives with beginnings, middles, and endings, bearing no resemblance to the fuzzy fragments of oxygen-starved hallucination. Patients reported reviewing their entire lives as a systematic assessment of their actions and intentions toward other people. They described seeing deceased relatives. They described a sensation of separating from their body and observing the room from above. And one of them proved it. In the first AWARE study, one patient described the events in his operating room during cardiac arrest. He identified specific visual and auditory details that occurred while his heart was stopped. The research team verified these details independently. They were accurate, and they were timed. The period of awareness corresponded to a 3-minute window during which the patient had no heartbeat and no measurable blood flow to the brain. 3 minutes. No heart, no blood, no oxygen reaching the neurons that supposedly produce every thought, every perception, every flicker of consciousness you have ever experienced. And this man was watching, listening, forming memories that he later recalled with precision. You could dismiss this as an anomaly. One patient, one case, possible confounds. But AWARE 2 went further. The 2023 study didn't rely only on patient reports. Parnia's team monitored EEG in real time during CPR, something no previous study had done at this scale. And what the EEG showed was, in some ways, more disturbing than the testimonies. 40% of the patients showed brain activity returning to normal patterns during CPR. Gamma waves, alpha waves, theta. The full spectrum of oscillations associated with higher cognitive function, the frequencies Borjigin found surging in her dying patients, the gamma oscillations Zemmar's Estonian recording captured. Except these patients were in the middle of CPR. Chest compressions, defibrillation, full cardiac arrest protocol. And their brains, in bursts, were producing the electrical signature of a conscious, functioning mind. Some of them showed this activity an hour into resuscitation. 60 minutes of clinical death. And the brain was still spiking with organized, high-frequency oscillations. Parnia's hypothesis for what's happening is the most unsettling thing a medical researcher has said in print in a long time. He proposed that the dying brain removes its own inhibitory systems, the brakes, the filters, the neural architecture that, during normal life, constrains your awareness to a narrow band of perception. When the brain dies, he wrote, it may open access to new dimensions of reality, including complete recall of all stored memories. Not because the brain is malfunctioning, because the systems that normally limit what you can access are shutting down, and in their absence, everything floods in. Every memory you've ever stored, every face, every voice, every room you've ever stood in, every meal you've ever eaten, every word that was ever said to you. All of it compressed into the neural tissue of your cortex, inaccessible during normal life because the brain's own regulatory systems keep the gates closed. And in death, the gates blow open. This is not fringe science. This is published in peer-reviewed journals. AWARE 1 in Resuscitation, AWARE 2 in the same journal, 2023. The EEG data is real. The patient testimonies are recorded. The 3-minute verified case is documented. And it raises a question that Parnia's data can't answer, but can't avoid either. If consciousness persists for 3 minutes without a heartbeat, if the brain can produce organized cognitive activity for an hour during CPR, then how long does it actually take to die? When does the last flicker happen? When does the final experience end? Every study we've discussed so far has measured what happens in the first minutes after the heart stops. The first 3 minutes. The first 5. The first 60 in Parnia's most extreme cases. But nobody has recorded what happens after. After the CPR fails. After the defibrillator is turned off. After the doctors leave the room. Nobody has mapped the brain's activity from that point, through the silence, through the fading, through whatever comes after the surge, to the actual, final, irreversible end. Nobody, that is, until a researcher in Paris decided to find out exactly where death begins. Not when. Where. In which neurons, in which layer of the cortex, and in which direction the end travels. Death has a geography. That sentence sounds wrong. Death is supposed to be an event, a moment, a line, a switch flipping from on to off. You're alive, then you're not. The heart stops, the brain follows, the person is gone. That's how medicine has treated it for centuries. That's how most people imagine it will happen. Séverine Mahon proved that's not how it works. Mahon is a researcher at the Paris Brain Institute, and in 2023, she published a paper that did something no study had done before. She mapped the physical path that death takes through the brain. Which neurons die first, which direction the dying spreads, and what the brain does in the space between the gamma surge and permanent silence. Here's what she found. After the heart stops, the sequence begins the way Borjigin and Zemmar documented it. There's the surge. Gamma waves, beta waves, the organized electrical storm that looks like heightened consciousness. This lasts seconds, maybe a minute, then it fades. And then comes the silence. The EEG goes flat, complete electrical quiet. The kind of reading that, in a hospital, would lead a doctor to look at the clock and note the time. The kind of silence that looks, from every external measurement, like the end. It's not the end, because from that silence, something emerges. Deep in the cortex, in a structure called layer 5, the largest neurons in the brain begin to depolarize. These are pyramidal neurons, massive cells with long axons that reach from the deepest layers of the cortex to the surface. They are the brain's heavy infrastructure, the backbone of cortical processing, and they are the most energy-hungry cells in the entire organ. When oxygen stops arriving, these neurons are the first to run out of fuel. Their ion pumps fail. The carefully maintained electrical gradient across their membranes collapses. The voltage difference that allows neurons to fire in controlled, meaningful patterns simply disappears. And when it collapses, it doesn't happen quietly. A wave of depolarization erupts from layer 5. Massive, high amplitude, visible on instruments as a slow, rolling tsunami of electrical discharge. Mahon's team watched it propagate in two directions simultaneously, upward toward the surface of the brain, and downward into the white matter, the deep cabling that connects brain regions to each other. She called it the wave of death. It spreads, slowly, methodically, the way a blackout rolls across a power grid. Region by region, the depolarization wave reaches neurons, overwhelms their remaining energy reserves, and silences them. The cortex goes dark from the inside out. Layer 5 first, then layer 4, layer 3, layer 2. The surface last. And in its wake, nothing. No gamma, no serotonin surge, no DMT cascade. The electrochemistry that produced the surge, all of Borjigin's data, all of Zemmar's recordings, that was the prelude. The wave is the finale. But Mahon found something else. Something that recasts everything we've just discussed. The wave can reverse. In her experiments, when oxygen was reintroduced to the brain shortly after the wave began, within a narrow window measured in minutes, the depolarization reversed. Neurons repolarized, ion gradients rebuilt, synaptic activity returned. The EEG climbed off the floor, brain function resumed. She called this the wave of resuscitation. It didn't always work. Out of 49 trials, 3 failed. 3 brains reached a point from which no amount of oxygen could bring them back. The wave had spread too far. The energy deficit was too deep. The neurons had crossed a physical line, measured in millimeters of cortical tissue, beyond which recovery was impossible. Which means death has a border, a literal, physical, measurable distance inside the brain. On one side, the wave of death is spreading. On the other side, the wave of resuscitation can still reach. And somewhere between them, in a zone measured in microns, in seconds, in a handful of ATP molecules, sits the actual point of no return. You can map it, you can time it, you can watch it approach. The data connects in a way none of these researchers intended. Remember the surge? The gamma waves, the DMT, the serotonin flood? The 300 times baseline activity that Borjigin found and Zemmar recorded. That surge happens before the wave. It happens in the window between cardiac arrest and the spreading depolarization. In the gap. In the space where the heart has stopped, but the wave hasn't started yet. The gamma surge happens in the space between life and permanent death. After the body has failed. Before the brain follows. In a window that, depending on temperature, oxygen reserves, and individual physiology, might last seconds, might last minutes, might, in Parnia's most extreme case, last an hour. The surge is not the brain dying. The surge is the brain doing something in the time it has left, before the wave arrives, before the border is crossed, before the point of no return erases everything. And for 46% of dying brains, nearly half, that something is the most intense neurological event of an entire lifetime. Mahon's wave tells us when death becomes irreversible. Borjigin's surge tells us what the brain does before that line is crossed. And Parnia's patients tell us that some people experience it, consciously, lucidly, with memories they bring back if their hearts restart in time. But that raises the question we started with 30 minutes ago. The question that none of these studies can answer, because none of them were designed to. In that window, between the surge and the wave, between the storm of gamma activity and the slow rolling blackout that follows, does your brain know what's happening? Is there a who inside the 300 times baseline? Inside the DMT flood? Inside the life review that Parnia's patients describe? Or is it all chemistry? Beautiful, complex, meaningless chemistry, performing for an empty room. Let's go back to the old man in Estonia, 87 years old, hooked to a machine that was watching for seizures. Heart stops without warning. And in the 30 seconds before and after that moment, his brain produced the most organized, most intense neurological activity of his entire life. Gamma oscillations, memory replay patterns, a brain coordinating across every frequency band it possessed. The machine was watching for seizures. It caught a man's brain replaying his life in the seconds around death. And one question has been sitting underneath all of this since we started. Replaying for whom? He was dead. His heart had stopped. The blood in his brain was slowing to a halt. Within minutes, Mahon's wave of death would begin its crawl from layer 5, rolling upward through his cortex, silencing neurons one by one. And in the shrinking window before that wave arrived, his brain was running a memory retrieval program with more coordination than it had shown during 87 years of waking life. If there was nobody home, if consciousness had already ended when the heart stopped, then the most complex brain activity of this man's life was a performance for an empty theater. A symphony playing to chairs with no one sitting in them. Billions of neurons coordinating their final act for no audience at all. That is one possibility. The other possibility is worse. 300 times baseline. When Borjigin's patient surged, gamma activity spiked to 300 times what the brain produced during normal consciousness. 300. Your brain has never operated at anything close to this intensity during your entire waking life. You have never thought as hard, perceived as vividly, or processed as much as your brain will process in the minutes after your heart stops. Your brain saves its best performance for the moment you can't witness it, or it saves its best performance for the moment you finally can. Parnia's patients didn't describe death as fading. They described clarity, the kind they'd never had while alive. A structured review of who they were and what they did with their time. A vividness that made normal waking life feel like looking through frosted glass. Parnia's hypothesis, published and peer-reviewed, is that this happens because the systems constraining consciousness are shutting down. The filters, the limiters. The neural architecture that evolved to keep you focused on survival, on the next meal, on the immediate threat. All of it goes offline when the brain begins to die. And in its absence, everything floods in. Every stored memory, every suppressed perception, everything you ever experienced but couldn't consciously access because your brain's own bureaucracy was in the way. If this is true, and it is an if, because we are standing at the edge of what neuroscience can prove, then the relationship between consciousness and the brain is not what we thought. We assumed the brain generates consciousness the way a generator produces electricity. Turn off the generator, the lights go out. But Parnia's data, Borjigin's surges, and Mahon's wave suggest something more like a dam holding back water. The dam doesn't create the water, it constrains it. And when the dam breaks, the flood is bigger than anything the dam ever allowed through. We don't know if this is right. The skeptics have their argument.